I'm going to do an example on how to use the Cauchy-Riemann equations to figure out where a function is differentiable. And I'm going to use these four functions here, where I map to x plus or minus y and x plus or minus y, where these pluses and minuses don't necessarily have to be the same thing. And so to use Cauchy-Riemann, one of the main facts is f is differentiable where one, we need the continuous, we need the partial derivatives, partials of u and v have to be continuous. Where, what do I mean by u and v? This part here is normally denoted u, and this part here is normally denoted v. So it's u plus iv is the function. And two, we also need these, both these equations hold. Ux of xy equals vy of xy. And we also need uy of xy equals negative vx xy. The way I think about these is if you go in alphabetical order, u and x come first, and then v and y come second, there's no penalty. If you switch the order, u and y, that's the first, u comes before v, but y comes after x, then you need the negative. That may or may not be helpful. So we're going to briefly see that in all these functions, the partials are going to be continuous, but these equations don't always hold. So let's just figure out these equations. U of x is always going to be equal to partial with respect to x. I'm going to do all four functions at once. This, but that's always going to equal 1. Ux is paired with vy, so I should also figure out what vy is right now. That's the partial with respect to y of this thing here. X plus or minus y, which equals plus or minus 1. So what we know, this implies that if we want there to be any chance of ever being differentiable, f of xy has to equal x plus or minus y. Don't know that one yet. But since I need this thing to equal that, this has to be a positive one, which means that the v part has to have x plus y. Like so. But now I can move on to the other equations. I can do uy and negative vx. And I'll just write down the negative sign here before I forget. Uy is equal to the partial with respect to y of x plus or minus y, and that's equal to plus or minus 1 because of the y. Similarly, this should be the partial with respect to x of negative, the negative comes from over here, x plus y. I know that it's x plus y from over here. And that's just going to equal negative 1. So I need these two things to be equal. Well, they're only going to be equal if this is actually negative 1. So this part needs to be negative 1. So I can set this equal to negative 1, which means that this has to be a minus sign. Which means that this all implies that I need f of x plus iy. That shouldn't be plus or minus. That should just be plus. Equals, well, I need a minus for the u part, and I need a plus for the v part. So this has to be x minus y plus I times x plus y. And if we do this, the partial derivatives, right, the partials are always going to be continuous because they're always equal to either 1 or minus 1. Ux is always equal to vy because they're both always equal to 1. Uy is always equal to negative vx because they're both always equal to negative 1. So they're always hold. So this is actually differentiable everywhere. This is differentiable everywhere. If it's differentiable everywhere, that means at every point on C, you can find an open disk around it that is differentiable everywhere in that disk. Because it's differentiable everywhere, it's going to be differentiable in the disk. So that implies that it's going to be holomorphic everywhere. And that's the basic idea behind the Cauchy-Riemann equation.